Okay. So just beginning with this, we'll just kind of get a little introduction into Dalton's atomic theory. So Dalton's atomic theories are still valid. And he had several rules on his atomic theory. One is that matter is composed of atoms, right? That all matter is composed of atoms, right? And what an atom was, he described what an atom was being the smallest unit of one element. Right? So we couldn't go any smaller than an atom. We can't get any smaller than an atom. And the second part of that is that elements consist of just one type of atom, right? So elements consist of only type of atom, right? And this is we're talking elements, not molecules. So in a molecule we'd have two different types of atoms. So if we look at water, water is H2O. We have hydrogen atoms, excuse me, and we have oxygen atoms. So we have two different types of atoms there. So elements, because elements are pure, we can't break them down anymore. That elements only consist of just one type of atom, right? The characteristics of the element are the same for every single atom there. So let's write that down. Characteristics of an element are the same for each atom. Now, atoms of an element uh, differ in its physical and chemical properties of other elements. Right? So atoms of an element differ in chemical and physical properties of other elements. All right. And four, compounds consist of atoms of two or more elements in a whole number ratio. So I'll write this down before I draw anything else out. So compounds consist of atoms of two or more elements in a whole number ratio. Um, and we should make a little note that the number of atoms is always same, right? So what we mean by this, so a compound consists of atoms of two or more elements, right? So it's not a compound unless I have two or more elements. So something like this is not a compound, right? Compound, this is just oxygen gas, right? That is not a compound. This is a molecule, but it's not a compound because I don't have two or more elements, right? So these compounds that exist with two or more elements, right, um, in a whole number ratio, right? So here is, here we go, two oxygens, or I'm sorry, two hydrogens and one oxygen, right? This is, everybody knows that this is water, right? But it exists in this compound in a whole number ratio, meaning that we can't do this. We can't break this down into one hydrogen and half an oxygen, right? This isn't how it works, right? That this compound only exists as H2O, that we can't break this down uh, into just one hydrogen and half an oxygen. And the number of atoms is always the same for water, right? This compound, H2O, this makes water, right? And it's always going to be the same. If I happen to add another oxygen, well, it's no longer water, right? The ratio here is a 2 to 1 ratio. There's two hydrogens for every one oxygen. And here, H2O2 is actually hydrogen peroxide, and this is a 2 to 2 ratio, right? So the ratio always has to be the same, right? A whole number ratio, the number of atoms always has to be the same, all right? Let's keep going here. Uh, the fifth theory he had is that atoms can't be created or destroyed. So atoms cannot be created or destroyed. So we can transform them, right? Uh, we can't ever destroy or create atoms. I should put during a chemical change, but they can make a different substance, right? So we can't create atoms, we can't destroy atoms, but the substance they make, the compound they can make, can definitely be different, right? So what do we mean by that? All right, so here is some hydrogen gas. So this little subscript here, G means gas, right? So here's a simple chemical reaction. We take some hydrogen gas, we take some oxygen gas, we add some energy to it. So I'm going to use this little triangle. This is going to be energy or heat, right? So if I put that into the reaction here, what we get is, this is a cursive L. So this is going to represent liquid. My writing's just fine. My wife's complaining. She knows by the end of the semester, you guys will all be experts in my writing. Right? All right. So atoms cannot be created or destroyed. So when we're looking at this, we see, well, I have two atoms of hydrogen. I have two atoms of hydrogen. I have two atoms of oxygen, but here I only have one atom of oxygen. So there is a fix for that, as we use these coefficients, and we're not going to get into much detail on these today. This is set for another chapter, but I just want to explain Dalton's law here and what he means by this, right? So I can fix this with what we call a coefficient, and if I put a number 2 here, right, that distributes to this, and now I have 2 oxygens, and it also distributes to this, which means I have 4 hydrogens, but there is another fix. I can put a 2 here, so that this represents what Dalton was talking about, right? Is that we can't create or destroy atoms, right? We can't just get rid of oxygen out of thin air, is that we do have to have some system in place in order to balance these reactions out, right? So again, we're not going to get into this, right? We're not going to get into balancing equations. This is just a simple idea in order to help you understand Dalton's theories here. All right. So what we have now is we have what we call the law of definite, the law of definite proportions, right? The law of definite proportions are what we consider constant compositions, right? Is that pure compounds contain elements in the same proportions by mass, right? So if we're looking at the mass of anything, if we look at it, they're always in the same proportion, right? So let's write that down. So pure compounds contain um, contain same elements in the same proportion by mass. The same proportion by mass. So need to flip around here. Right. So we see isooctane here. Let me draw isooctane out for you. So isooctane looks like this. How to draw isooctane? There we go. There we go. So this is what we consider isooctane. So isooctane has a mass ratio between carbons and hydrogens of 5.3 to 1, right? And you can take different sample sizes. Doesn't really matter what the sample size is, but you can see here that we have 3 samples, and as they measure out the mass of these samples, they measure out the mass of the carbon, measure out the mass of the hydrogen, and it always comes out with this 5.3 ratio, right? And this happens with any pure compound. So any pure compound, whether it's propane, octane, water, uh, is that it will always the mass ratio between the elements is always at some set ratio, right? Is always going to be at some set ratio. So that's what we consider the law of definite proportions, the law of constant composition, is it really doesn't matter what it is, if it's a pure compound, that the mass proportions are always going to be the same. Okay, let me say goodbye to my wife real quick. All right. Then we have something else that's slightly different. We have what's called the law of multiple, the law of multiple proportions. All right. So the law of multiple proportions happens when two elements react, right? Um, and they form more than one compound. All right. So when multiple proportions um, is when two elements react to form then pound. All right. That a fixed mass of one of the elements will react with the mass uh, of another element in in a certain ratio. All right. So I have a couple of examples of that and some calculations that we can simple calculations that we can go over along with some pictures here, some images. So what do we mean by this law of multiple proportions, right? Is that we have two different substances here. One's this green substance on the left, and then this brown substance on the right, and they're both made of copper and chlorine atoms, right? So the green mixture there, so between copper and chlorine, so between copper and chlorine there, we had this green substance, and then we had this brown substance, right? So this green substance, there's a ratio between the copper and the chlorine that is 0.558 to 1. While the brown chlorine is 1.116 to 1. Right, when we're looking at those. So and we're not talking about, and don't confuse, because I know we said whole number ratios, right? Whole number ratios. But we're not talking about atoms right now. Is we're talking about the mass of these. So this is why they're not in whole numbers, okay? So there is a difference there, because I don't want you to get confused law of multiple proportions with Dalton's laws, right? When we talk about Dalton's laws, H2O, we had to have some whole number. H2O is 2 to 1, right? And we'll see that Dalton's law when we're looking at the law of multiple proportions, okay? So these mixtures here, these compounds here, right? The green one, the mass of it is 0.558 to 1, right? So we get 0.558 grams of chlorine for every 1 gram of copper. For that brown substance here, well, for the brown substance, it's closer to a 1-to-1 ratio, that it's actually 0.116 grams of chlorine for every 1 gram of copper, right? So it's more evened out on that side. And if we wanted to take a look at it, is that we could look at it this way and say if we have 1.6 grams of chlorine over gram of copper, and we actually divide this by 0.558 grams of chlorine for every 1 gram of copper, is that we will get a whole number ratio, right? We get a whole number ratio where we get a 2-to-1 ratio here. 2 atoms of chlorine for every 1 atom of copper, right? So we see Dalton's law here really taking effect here, that it does work out when we use this law of multiple proportions. Let's actually take a practice. Let's look at another problem here. So if I were to give you uh, 3 different compounds, we'll call it compound A, compound B, and compound C, right? We'll say that compound A is 2.28 grams of carbon and 0.19 grams of hydrogen. All right. And compound B, when we weighed it, was 1.62 grams of carbon and 0.27 grams of hydrogen. And compound C was 5.16 grams of carbon and 0.43 grams of hydrogen. All right. All right. So let's first figure out the ratio here, right? So let's figure out the ratio, and we're going to take a look and see if we can define the law of definite proportions and the law of multiple proportions by using some of this information that we have here. All right. So first, if we just take this information here, we go 2.28 over 0.19, right? Well, let's see what that equals. And you guys calculate that out. Tell me what you get when you. I'm not going to do the calc. You guys do the calculations. I already know how to calculate it.
I got 12.
Yes, it is 12. So here we have a 12-to-1 ratio. Okay. Um, and if we do the same thing here, we'll have, I'm going to put it in a different color here. We got 1.62 over 0.27. And what do we get?
I got 6.
6. So that is a 6 and I'm going to do it this way instead. So we'll put 12-to-1 ratio. This is going to be a 6-to-1 ratio. And then the last one,
12 again.
all right. And we have a 12-to-1 ratio. Okay, so by looking at this, the 12-to-1, 6-to-1, 12-to-1 ratio, when we look at compounds, so we've measured these out here. Let's take a look here. Is that compound A and compound C are both 12-to-1 ratios, is that we have different masses of these, but yet the ratio is coming out the same. And when we talk about that, well, we've just discussed that in the law of definite proportions, is that it doesn't really matter what the mass ratio is, right? When we do this, right? So we're talking 12-to-1 ratio, and they're both being 12-to-1 ratio. Is that, oh, where's the image that we had here? Right? When we talk about the law of constant composition, that mass ratio is the same. Doesn't really matter what the masses are, is that the mass ratio ends up being the same. So we could say, looking at this, is that both A and C support the law of definite proportions. The law of definite proportions. Okay, well, now let's take a look at this information still here. All right, so what if we take the mass ratio of these? So what if we take, let's see, how about we take 2.28 grams of carbon over 0.19 grams of hydrogen, and we divide that by B, 1.62 grams of carbon over 0.27 grams of hydrogen. All right. And what do we get from that?
I got 2.
2. So here, and let me put this here, 2 over 1, right? We get 2 to 1, right? And this is from, this is A, this is B. And let's see, we could do it because I'm looking at these ratios here. Oh my gosh, I wish it would stop doing that. Because I'm looking at this information here. So we did this and this. Well, let's now do this and this. So let's do C and B. So if we have C and B, we have 5.16 over 0.43 divided by 1.62 over 0.27. And what do we get? One, two students. Let's go.
2 as well.
2 as well. All right. So again, another 2 to 1 ratio. So by dividing these mass to charge ratios, I'm sorry, not mass to charge ratio, by dividing these ratios here, so we see it here where we have the law of multiple proportions. So both of these laws have been supported both by ideas here, by some figures, as well as some simple math that we did. So here, we'll say that this one down here would support the law of multiple proportions, right? I would definitely, keep an eye on that one because you're definitely going to see something like that on the exam. All right, let's take a look at this here. So this is a cathode ray tube. And where it says cathode and anode, right, these are electrodes. We're going to have some electrical charge placed in between both of those cathodes there, both of those electrodes there, right? And what it does, and this is an early experiment by Thomson, and what it did is it created this beam of light. But in this cathode ray tube, there is no air in here, right? So they vacuumed out all the air. They put this charge between two electrodes, the cathode and the anode, and they were able to make this beam of light that reached the other end of the tube. So they thought it'd be interesting. So this is an electric charge that's doing that. Well, what they decided to do is if you look here at this portion here, where it says positive, negative, those are positive and negative ends of a magnet, right? Magnets have this north pole, south pole. So they have these plates here, and the plates now have a magnetic charge. So as this beam of light, before the magnets, if there's no charge on those magnets at all, it just hits this end right here, and it goes straight through. But once they turned on those magnetic plates, it changed the angle of that beam. And they tried to understand, like, why was this going on? Why was this going on? When we charge these plates, why does the light bend this way? So based on all these observations, came the idea of the electron. The reason it was bending was because they, based on these observations, is that they found out that the electron had a charge on it, right? When you put two things that are positively charged together, they repel. Two things that are negatively charged, they repel. So looking at this here, the reason that it went in this upward direction is they deduced that, well, electrons must have some negative charge on it. It's got a negative charge and it's attracted to the positive magnetic plate, right? Not the negative magnetic plate. If it had been, if light had gone the other way, then they would have said, well, electrons have some positive charge, but that wasn't the case on there. So electrons, right, are, and let's write some definition down here. Subatomic particle that is negatively charged, and the mass of this is just 10,000 times smaller than the mass of one atom, right? But a subatomic particle, it's a subatomic particle that is negatively charged, right? So looking at another experiment, coming off of Thomson's experiments, is Millikan used this here because they wanted to calculate the charge, right? They wanted to calculate the charge of an electron. Well, they can't actually pull an electron off and measure the charge on it, but what they were able to do is that they were actually able to have an X-ray hit some oil droplets and able to determine some charge by that. And they found out is that, so we have all these oil drops, right? And the drops were not all the same size, right? We can't get in a drop of oil to always be exactly the same size. But what they did find out is they did calculate the charge of the droplet, and they always seem to be some multiple of this. It was always some multiple of 1.6 times 10 to the minus 19, right? Here, right? 4.8 times 10 to the minus 19 is 3 times 1.6 times 10 to the minus 19, right? 6.4 times 10 to the minus 19 is 4 times 1.6 times 10 to the minus 19. So it always ended up being some multiple of that number. 1.6 times 10 to the minus 19 coulombs. So in Millikan's experiment, right, the droplets, put oil droplets, were always a multiple of 1.6. And do they have, yeah, my notes here. Yeah, that's fine. Okay. 1.6 times 10 to the minus 19. And that capital C is coulombs. Well, please don't make me cough. Please don't let me cough. All right, I think I'm good. I was about to have an attack there. All right, C for coulombs. All right. So what they decide is that because every droplet was some multiple of this, is that this was going to be the charge. That's what they determined the charge of an electron to be. So the charge of an electron, write out electron. Too soon for my shorthand, probably. 1.6 times 10 to the minus 19 coulombs. Uh, you have to memorize that number. Yeah, you absolutely have to memorize that number. I'm not giving you this value. Um, so then, between Thomson's research and Millikan's research, is that they were able to determine a charge to mass ratio, right? So we'll say this charge to mass ratio ended up being, excuse me, come on, 1.759 times 10 to the 11 coulombs per kilogram. I'm going to pause this real quick.
Professor.
I didn't even unmute myself. My gosh.
Okay.
Thank you for that. I'm sitting here talking to myself. All right. So did we, I probably have to go over this charge to rate. Nobody was hearing me when I talked about charge to mass ratio.
No.
Ah, all right. So here it is. So with all the information that Dalton and Thomson had provided, is that they were actually able to calculate the mass of an electron, right? So using the information uh, here regarding the charge to mass ratio and using the charge of an electron that we were able to get, is that they were actually able to take that information, and here it is okay to use reciprocal values. Anytime that we have some conversion factor, something that we're trying to cross cancel out, we're chemists. We have the absolute right to use reciprocal values anytime we need. Okay. If I need to cancel something out and it doesn't work the way it looks, I'm going to flip it around and then use it that way, right? It's our right as chemists. And we see we end up with some value here on just how much an electron weighs, right? And if you ever see this E with the little negative symbol up there, that's just my shorthand for an electron. All right, so now getting into the actual atom, um, I don't eat plum pudding, but I don't even know anybody that does eat plum pudding. I've never even seen it before. But this is what plum pudding is, and this was just kind of the first idea of what an atom looks like. Is that an atom had some positively charged matter, had some negatively charged matter, and it was all, so an atom was just filled up with this. They don't even know what it was filled up with, and inside of there we had, all these positively charged particles, and then we had a bunch of just negatively charged particles, and that was just kind of the first idea that came across, that like this is probably what it looks like. But then after some more observations, is that they're trying to understand that there's actually a lot of space. So this came later. After that, it came later that maybe there's a center, maybe there's some nucleus there with some positive charged particles, and then around that is where we have our electrons that are all negatively charged, right? And that came out later. But you'll notice that, I mean, atoms really do have a lot of empty space. This is just empty space, right? And they use the idea of a football stadium and blueberries, right? So if you can imagine a football stadium as being the atom, is that the blueberry would be the nucleus, right? And the rest of it's just going to be filled up with electrons spinning around that nucleus, right? So that's just kind of an analogy that's always used in order to understand just how much empty space an atom really has. So uh, after after some time, they actually now started to look at because we need to determine some information here, is that we know how much an electron weighs now, and they now had to determine, well, how about these protons, what they call them protons, right? These are the other subatomic particles that are positively charged, and we end up calling those protons. And the nucleus here, the protons are also mixed with something we call neutrons, another subatomic particle. And another unit was developed out of this, something that we call the atomic mass unit, and we'll use AMU for short, right? So the atomic mass unit was based on what we call carbon 12. Carbon 12 is what we call an isotope, and we'll get into isotopes in just a little bit, but I will tell you that this number 12, carbon 12 is based on a certain isotope, which is the most abundant isotope, right? Um, we have stuff like carbon 13, carbon 11, and they weigh differently, but as far as the most abundant isotope on the planet, carbon 12 is the most abundant isotope, right? And again, we'll get into isotopes in just a little bit. So this new unit, atomic mass units, were based on what we call carbon 12. And let me write that down, the most abundant isotope. All right. Is that they wanted this really needs to be really accurate. They used to base it off of hydrogen, um, but it just wasn't accurate because hydrogen had another isotope, uh, and it just really wasn't a good use for the atomic mass unit. But one atomic mass unit, let me write it down. So one AMU is equal to 1/12 of carbon 12, right? That was what one AMU was equal to 1/12 of carbon 12. And one AMU, let me write this in a different color. AMU is equal to 1.6605 times 10 to the minus 24 grams. So as far as something that we can understand because we're familiar with grams, this is how much one AMU weighs. One AMU is equal to 1.6605 times 10 to the minus 24 grams. And that one proton, and this is my shorthand for proton, is the P with a positive symbol there. One proton is equal to 1.0073 atomic mass units. And let's see what we're going to call in the nucleus here, right? In our nucleus, our nucleus is composed of protons and what we're going to call neutrons. And it happens that one neutron, and this is my shorthand for neutron. Uh, looks like an H there. Should be N. This is my shorthand for neutron. So my shorthand for neutron, and that weighs 1.0087 AMU. All right, so looking at that, so we have two new subatomic particles, right? We have two new subatomic particles, and let me write down the electron here. So one electron plus my little shorthand for that weighs, an electron weighs 0.00055 AMU. It's really nowhere, and it's not even the same ballpark of what a proton and what a neutron weighs. So I put the positive on a proton because protons are associated with some positive charge. Electrons are associated with some negative charge, and neutrons aren't associated with any charge. right? That there is no charge associated with a neutron. But we can see from this, is that protons are almost the same mass as a neutron, right? Protons and neutrons are almost the same, right? And we can definitely see just from this is that an electron is not just less than a proton, but it's actually a lot less, right? Is that electrons weigh a lot less than a proton. Is that it takes about 1,800 electrons to almost equal one proton. So considering that information, right? So it takes 1,800 electrons to equal just one proton, right? And with the periodic table, I believe we are at, oh, let's see, what is the newest element? Os, organ, Organicin? Yeah, it's like 118. So the heaviest element, the element with the most number of electrons, is 118. And you need 1,800 electrons to even count for the mass of just one proton. So when we're looking at the mass of an atom, we only consider two things. We consider the mass of the proton, we consider the mass of the neutron, and we do not consider the mass of an electron, simply because they just don't weigh enough to make any significant difference in the mass of the atom. So the number of protons. So the number of protons in the nucleus uh, of an atom is its, no, possessive, is its atomic number, right? Every element on the periodic table has an atomic number. And the atomic number, let's see if we can just bring up some generic periodic table here. Right? You'll see that every single, so these atomic numbers, you'll see them in the top left-hand corner, like hydrogen, right? Hydrogen's 1, lithium is 3, beryllium is 4, right? It's not in order of discovery, right? This wasn't made in order of discovery. Oh, we discovered hydrogen first, so that gets number 1. No, that's not how these numbers work. So these numbers work, these are what we call atomic numbers. And you'll see that no two elements on the periodic table have the same atomic number. They're all unique, every single one of them. And the atomic number is based off of how many protons that specific element has. Iron has the symbol of Fe, atomic number 26, meaning it has 26 protons. Nickel, number 28, means that nickel has 28 protons, right? Here's lead, which is Pb. Lead has, each one of those atoms have 82 protons. So the atomic number, we use a symbol for the atomic number. And the atomic number, we use this Z to represent atomic number, right? So the atomic number is the number of protons. Now, the mass of an atom is represented by this letter A, right? Now, the mass of an atom, because we've just talked about this, we talk about the nucleus, and the nucleus is going to be the mass of the atom. We don't consider the electrons, just what's in the nucleus, and those are protons and neutrons. And we need the mass of both of those. So the mass of an atom is equal to the number of protons plus the number of neutrons. Well, how are we going to know how many neutrons there are? Because if you take a look at this periodic table, right, uh, we don't tell you how many uh, protons or how many neutrons are there. Let's take a look at. All right. So we see these bottom values, right? So the top value, right? So iron is Fe, and we see that top value 26. That's the number of protons. The bottom value, and we are going to round these, right? So the bottom value is about 56. And there's a reason why they're going to be rounded, okay? So there is a reason why they're rounded. An atomic mass unit doesn't exactly weigh one atomic mass unit, right? I'm sorry, a proton doesn't weigh exactly one atomic mass unit. It's 1.0073, right? For a neutron, it's 1.0087, right? So we do get these other values here, but we can round these to determine how many neutrons we have. So iron, which is 56, I'm going to call it 56. So if we take a look at these, if we take A, which is the mass, and subtract it from Z, which is the number of protons, this is your number of neutrons. So iron had a mass of, or had atomic number 26 is what we saw. So it has 26 protons, and the mass of that was 56. Well, we simply take A, the mass, minus 26. 56 minus 26 is 30, which means there are 30 neutrons. Iron has 26 protons, and it has 30 neutrons. Okay, so that's how we determine that. The number of electrons, if we take a look at everything on the periodic table, we consider everything here to be neutral. Everything on the periodic table is neutral. And why is the number also not on the table? There's only so much information we can put on a periodic table. If you're a scientist, if you're a chemist, and what I just taught you, from what I just taught you, is it necessary to put the number of neutrons on the periodic table? If you looked at,
It's not necessary. I'm just thinking
right?
if it would be
No,
easier
no,
if
yeah, no, you're absolutely correct. Like this is the reason. I'm trying to answer your question. I'm not trying to belittle you or anything like that. I'm
no,
not.
I understand.
I'm just, if there's only so much information we can put on a periodic table,
Yeah.
and we have to make it clean. And if we start putting all these numbers, just like the number of electrons, the number of electrons aren't here, but I
Mhm.
will tell you how to get it. Just
Yes.
like I showed you the number of neutrons. So, again, there's only so much information. So they could put it, maybe a subscript somewhere, but with these little boxes, again, there's only so much information they can put on there. So
Mhm.
there's information that's omitted, but this is why I teach you where to get this information,
Mhm.
right? So, but that's the reason. It's just those little squares there on the periodic table, there's really just so much information they can put on there. So we have to make a simple calculation. And as far as the electron goes, one positive charge will balance out one negative charge, which means that if I have 26 positive charges coming from the protons here, well, how many negative charges do I need to balance that? I need 26 electrons, right? So the number of protons is equal to the number of electrons. So this can now be done, this simple math can now be done um, for any element. Is that, let's take a look at, I used to work with, excuse me, I used to work with iridium a lot when I was in grad school. So here's iridium. Iridium 77 and 192, right? So I'm rounding that. So we have iridium, which mass is 192. So we'll write that down. Iridium has a mass of 192, and the number of protons is equal to 77. Well, let's see. So if the number of protons is equal to 77, that means the number of electrons is how many?
77.
77. And if I want to take the number of neutrons, well, 192 minus 77. Anybody?
115.
Correct. 115 neutrons. Right? So now we can actually get some of these values, right? So now we have some values that we can actually calculate. And when we're looking at in your books, you're going to see it this way here. I'm going to write a generic version. So you'll see X. No, you won't see X, but I'm going to put this here and explain what all of this means here, right? So X, this is going to represent your element, right? We already know what A is. A is equal to the mass, and Z is equal to the number of protons, but it's also equal to, and let me put that down as well. Um, I'll put the atomic number. The atomic number, which is also equal to the number of protons. So if we were to write iron, we would write iron this way. Iron, here's Fe. The mass of it was 56, and the atomic number was 26, right? Iridium. If we were to write iridium, I'd put IR here. It weighs, or the mass is 192, and the number of protons is the atomic number, and that is 77. So this is how you're going to see it in your book, and there's probably plenty of examples when you start seeing it like that in your in your text. Let's see. Yeah, so here. So we'll get into the charge in just a little bit. That's kind of our next area where we're going to. But here you'll see, we see everything here, right? So as far as boron goes, boron weighs 10 atomic mass units and has 5 protons, right? And this is what we would call boron 10. But then we see, this is where we get into isotopes here. Isotopes weigh differently. So isotopes have either one less neutron or one more neutron, can have 3 more neutrons or 3 less neutrons, but these are what we call isotopes. So here we see carbon 12 I told you about because it has 6 protons, 6 neutrons. Carbon 13 has 6 protons, 7 neutrons. Carbon 14 has um, 6 protons, 8 neutrons. right? So these are what we call isotopes. Isotopes have are the same element, but a different number of neutrons. So isotopes are the same element with a different number of neutrons, right? Isotopes are the same element with a different number of neutrons. And if we look at the very last column here, the last column is our what we call natural abundance. And this is the percentage of how much we find just naturally. So as far as carbon-12 goes, you'll see carbon-12. Carbon-12, out of all of the carbon that exists here on Earth, is that 98.89% of all of that carbon is carbon-12. 1.11% of carbon is carbon-13 with an additional neutron. So these are the different abundances. So as far as carbon-12, carbon-13 goes, it's not 50-50. It's not 50% carbon-12, 50% carbon-13. Is that we have these different natural abundances of each one of these different isotopes that we have. All right. So as far as ions go, so now as far as electrons and ions, so let's start as kind of a different section here. We're talking about ions. So ions are atoms that have an electrical charge, right? Are atoms that have an electrical charge. Could be positive, could be negative charge, right? And that will all just depend on what's going on with the electrons there. So we can vary the number of neutrons and we get isotopes. We can vary the number of electrons and we get ions, right? But we never vary the number of protons. The number of protons is unique to every single element out there, right? Every single element out there has its own atomic number, and that's the number. So if we increase or decrease the number of protons, well, we completely change the element. Here's iron. If we get another atom or another proton into iron, well, we don't have iron anymore. We have 27 protons, which means we have cobalt. Take a proton away, well, we don't have iron anymore. We have manganese, right? So we never vary the number of protons, but we can vary the number of neutrons, which I just showed you in the isotopes, and we can also vary the electrons, which provide us ions, right? So say this is sodium, right? Sodium has 11 protons, which means that sodium also carries 11 electrons. And when we look at the overall charge here, the 11 protons cancel out the 11 electrons, and we just have some zero charge here. But what would happen if maybe we take away an electron? So we take away an electron, and now we only have 10 electrons. We can see that the charge is not balanced anymore. Is that, do I have more negative charge or more positive charge according to how many protons and electrons I have? Well, I have more positively charged particles. I have more protons than electrons. Protons are positively charged, so I have an additional positive charge on that. And we represent that, and we're going to put that as a symbol up. You're going to put that up here and say that sodium has a positive charge here because it only has 10 electrons. So you can write it like this, or you can write it like this. It doesn't really matter. You could just maybe put the Na plus. It means the exact same thing. And anything with a positive charge, so we'll say that positively charged ions are what we call cations, right? Positively charged atoms or ions are what we call cations. Let's do one more here. Iron. Iron we know has 26 protons, which means it has 26 electrons. Well, again, we have zero charge here. Let's take away 2 electrons. We have iron with 26 protons, but if I happen to take away 2 electrons, right, now we're going to have 24 electrons, and we can see that, well, we have more protons that are positively charged, and we have 2 more of those. So we actually end up with an overall charge of positive 2, and again, we put that here, and we'll say positive 2. Let's see, we can continue. What if we take more away? What if we did 26 protons and 23 electrons, right? Well, now we have a difference of positive 3, and we can note that here and say that's going to be 3 plus, right? Is that this iron is a cation with a positive 3 charge because it's got 3 more protons than it does electrons. Then we can look at something like this. How about we take a look at oxygen, which is different here. Oxygen, right, has 8 protons. So we go 8 protons, which means it has 8 electrons, and there's no charge on that. But oxygen, instead of taking away electrons, how about we add some electrons? How about we add 2 electrons, and that gives us now 10 electrons. And we see that, well, this is different now. Now electrons are negatively charged, and I have more negative than I do positive protons. And I have a difference of 2 electrons, a charge of negative 2, right? So we also represent that here as well. And I'm going to put that here, and we'll say that that's 2 minus. So this oxygen is negatively charged. And negatively charged ions are called anions. Anions. Well, let's do one more here about chlorine. Chlorine has 17 protons, 17 electrons. But if I happen to take away, or let me add one other electron here. We'll say 17 protons, but 18 electrons, right? Is that I have some negative charge here of just -1. And we do put 1 minus, not -1. We put 1 minus. So we put the charge up here, 1 minus, or we can write it as Cl, just negative, either one. Both of those are going to be the same answer. But we do put the number and then the charge, right? So here we do this. We don't do this, right? That's wrong. We don't do that. We put 2 and then the charge on there, 3 and then the charge on there, whatever that happens to be. All right, just where I want it to be, but I have to mute myself real quick. All right, sorry about that. Okay, so I think we're just, I hope I have time to, I don't know if I'm going to have time to finish this, but let's see. I don't want to rush through it. So isotopes, when we take a look at isotopes, they vary in the number of neutrons. And when we take a look at these, I do have to show you this. All right. So let's take a look at go here. Let's take a look at boron. So boron, you see, is 10.811, right? 10.811. But when we look at here, well, we get 10.01 and 11.00. Well, oh man, I'm not going to make it here. All right, so everything on the periodic table, all of those masses are weighted averages. They're weighted averages. So what we have to do is we have to learn how to calculate the average atomic mass. So we're going to learn how to calculate this atomic mass that they have on the periodic tables. So if we take a look at, we're going to use magnesium here. So we'll use magnesium 24, magnesium 25, and magnesium 26. So the mass, and this is going to be an AMU, the mass of magnesium 24 is 23.98. The mass of magnesium 25, 24.99. And the mass of magnesium 26 is 25.98. All right. So here, the absorbance, right? Not the absorbance, abundance. So the percent abundance on these, magnesium 24 is 78.70%, right? So out of all the magnesium out there, 78.70% is magnesium 24. Magnesium 25 comes to 10.13%. Oh, not 10.13%. And then we have 11.17% for magnesium 25 or 26. In order to calculate the average, right? If I gave you this value here, if I gave you 1, 2, and 3. If we had to calculate this, right? So if we had to get the average of these numbers 1, 2, and 3, how would we get this average, right? This is how you would get the average. So you would add them all up, and this is equal to 6, and then you divide it by 3, and the average number is 2, right? Yeah, don't do that. That's not how we do the average here, right? We don't just simply add them up divided by however many we have, right? We can't do that because the percent abundances are not 33, 33, 33, right? So we have to take those percentages into account. We have to do what's called a weighted average. So the way we do the weighted average is we're going to actually multiply the AMU and the percent abundance, but we can't multiply decimal notation 23.98, and percent notation. We have to convert percent into decimal notation so that we can then multiply those two together, right? So this is going to be converted to 0.7870. How did I do that? Divide by 100, right? So this is going to be 0.1013, and this is 0.1117. And now we're going to take those, and now we're going to multiply the masses of those, right? So this times 23.98, and you guys can start calculating those 24.99 and 25.98, and you're going to give me those values. So either type it out or let me know what you get.
For the first one, I got 18.87226.
18.23.98 times 7870. Does anybody did it? You said
87226.
87226.
I
Yeah,
got the
that's fine. Yep, that's fine. Okay, and the next one?
2.531487.
And the last one.
2.901966.
So now to get the average, the only thing we need to do is let's take all of these values and we're going to add them together. So add those together and what do we get? And let's just do it to, we'll just round it to 4 sig figs, is fine. One person really shouldn't be answering these, so, you know, just make sure you guys have calculators ready.
24.31.
24.31 AMU. Let's see if that matches. 24.31 magnesium, 24.3050, which if we rounded that would be 24.31. So we've learned how to calculate the weighted average of that, right? We're not going to get into it today, but when we come back, we're going to calculate the percent abundance, right? And we'll do that when we come back. That's kind of lengthy. There's some understandings. There's some math manipulation that we need to do there. And then we'll continue on with the rest of that chapter. We actually might finish the chapter early, and then if that's the case, we'll jump into Unit 3 earlier than I expected to. Other than that, yeah, other than that, I think we're probably just going to stop here.
Can you go